Hello, this is Dr. Hasan Abdullah with the course Introduction to Natural Language Processing. And the topic which we are covering is language model. So this is the ninth topic in our course outline. And the subtopic is hidden Markov model and generative pre-trained transformer GPT. So that's why it's lecture 9B. So this lecture is based upon and uses the supplemental material available at easymcq.com/goget, which basically is a learning management system. And of course, it is a personalized learning management system because it allows you to personalize your route to the required level of learning. So you're not fixed or to a certain sequence of learning. And of course, you can also personalize it by searching through all the question and answers in all the courses. So as you know that the concepts are presented in the form of questions to challenge your imagination, and then there are the detailed answers. When you perform a search, the keywords are highlighted, so it can be preserving the order of keywords or the free order of keywords. So so how do you do that? For that learning route, you look at video number 1. And how do you perform these searches? You look at video number 3. And you can personalize the appearance or the interface as per your need or liking. How do you do that? That's in video number 4. And you can personalize the online exams also, which supports online testing and grading and analysis of results of all the exams which you have taken. So how do you do that? That's shown in video number 5. So these videos along with this course video and the videos of all the courses, they are available on my YouTube channel and also available on Canvas. To view those videos, you go to YouTube and enter search with my name, Dr. Hasan Abdullah, and you will come across and you can access those videos. So the topics which we are covering in this course are in front of you, and the topic of this video is language model. So let's move on to the supplemental website. So we are now at the supplemental website. The first 5 concepts in the form of questions were covered in lecture 9A. So now we are at the next set of concepts in the form of questions with detailed answers, which is video 9B. So the question is in front of you. So we would like to fill this blank using the hidden Markov model used as a language modeling. Okay. So what are the steps involved? So we are interested in the steps. So let's look at those steps. And in the next question, you will see that the complete working. So the steps which are shown here, the working of those steps will be shown in the next question with detailed working. So what are the steps, okay, which we'll be covering as an answer to this question? So first of all, need to understand the problem. All right. So once there is an understanding of the problem, then very briefly touch upon the hidden Markov model, basics of it. That what is hidden and what is not hidden. Basically, what is hidden is are the tags. The tags are hidden, and what is visible is the words. So what are the steps to solve the problem, which is the language model using HMM? Define the states and the observations. What is the state? What is the observations? We define them. Train the HMM, training based upon the corpus. Of course, we will not be using any corpus here. I'll give you certain idea, okay, which makes sense. So then we use the Word2Vec algorithm to, as a matter of fact, identify the sequence of the hidden states and then make the prediction about the missing words. Which missing word? The word which will go here. That missing word. So now let's look at the details and what are those steps in detail. So understand the problem. So we have the sentence, okay, and there is a missing word, and which there's the missing word, okay. So what is the goal? The goal is to predict the most likely word to fill the blank, okay, using what? HMM based language model. So what is the hidden Markov model? Hidden Markov model basically is statistical in nature, and we assume that it follows the Markov process. What is the Markov process? The Markov process is the next state is dependent only upon the current state. So what we have the states, observations, transition probabilities, emission probability. What are the states? States are the tags: noun, verb, adjective. Okay, these tags are the hidden tags or the hidden states. And what are the observations? The observations which is visible is the words which we see in the sentence. For example, the child is going to. These are the observations. And tags are the hidden, isn't hidden. Okay. So transition probability is the probability of moving from one state to another state. These are the transition. These are calculated based upon the corpus. emission probabilities, the probability of a word being emitted from a state. So once we have identified a state, then what would be the word corresponding to that state? That goes to fill the blank here. So what are the steps to solve this using HMM? We proceed by we define the states, okay, and what are the states with the parts of speech? Noun, verb, adjective, pronoun, adverb, and so on. There are 30 of them, which I believe I showed you in the beginning of this course. The matter, there can be more than 30. And what are the observations? These are the tokens basically. All right. So how do we train the hidden Markov model? These are the conditional probabilities. These are the conditional probabilities. So what is the probability of getting into state I in the context condition upon the state I minus 1? And what is the probability of getting the next word in the context of or based upon the state, whatever that state may be? And then we use the Viterbi algorithm. So what is the Viterbi algorithm? What is the most likely sequence of hidden states? What are the hidden states? Part of speech tags. So once we have that tag, okay, then we calculate that what is the word corresponding condition to that tag, right? So for the sentence, okay, we predict the most likely part of speech tag for the blank, okay, and then the most likely word corresponding to that tag. That I'll show you in the next question. And then we predict the missing word, and which is have the highest emission probability. So when we look at the highest emission probability, basically it's greedy approach. Remember that. And the greedy approach is based upon the current state, not and of course it does not take into consideration what will be the consequences of making that decision. All right, that's the way it is. So if you're interested, you have more reference to read. So give the complete working of using HMM for modeling, okay, and predicting the next word. Which word we are talking about? The word which goes to the blank here. So what we'll do, I'll show you the transition probabilities, emission probabilities, and then use the Viterbi algorithm to make the prediction. All right. So we assume something. We assume, okay, that what are the transition probabilities and what are the emission probabilities. Of course, this is assumption for simplicity. Otherwise, we'll use the corpus, whatever that may be, which you select, and based upon those, the contents of the corpus, the transition probabilities are calculated. So what this says is that what is the probability of the next word to be a verb in the context of the word to being used. So based upon, we assume that it's 0.8. And what is the probability of the next word or the predicted word to be a noun conditioned upon in the context of the word to is 0.2. Okay. Similarly, if the word is a verb, right, then what is the probability of that verb to be a play? Okay, so play is a verb, and of course sleep is also a verb. And what is the probability if the current tag is of a noun? Okay, and based upon that tag, the probability that you have a park as a noun, 0.2 probability. All right, so let's look at the Viterbi algorithm. So we see that in our statement here over here, before the blank there is the word to, okay, and that word to is followed by a noun or a verb. That is followed by a noun or a verb here. Let me change the pen for improving comprehension. Okay, right. So 2 and 2 and 0.8 and 0.2. So with the verb we have the 0.6 with the verb, and with the verb we also have 0.3. So if the blank is a verb, what is the conditional probability that if it is a verb, okay, and then the next the word would be play, that is 0.8, this 0.8, and this 0.6. You have 0.48. And similarly, what if it is a noun? Okay, so then the probability is 0.08. So we see that the verb option has a higher probability as compared to the noun option. Okay, so we say that the word which will follow to would be play. That would be play. Okay, let me clean this. So what we have as a final answer, before we go to the final answer, what we need to see is that we have a greedy approach. Why we use a greedy approach? Because it's simple, right? It's very simple to implement, right? And more, and it's but the problem, and we therefore we select the highest probability. And why it is simple? Because the computational complexity is low, is efficient, okay, but it results into suboptimal sequences. Means that it may result into wrong answers also, wrong assignment also. But right now we pick the word with the highest probability, which is play. So in the blank space we will get play. The child is going to play. So this is based upon the hidden Markov model. All right. Okay. So this is the summary, and this is the diagram, which basically is the this basically what it shows. This is the conditional probability for this. What is the probability of getting the word based upon the sentence as the child is going to? This is left blank. Okay, so this conditional probability and these probabilities are calculated based upon the corpus, and we can see that the probability of play is the highest among all of them, right? It should have been actually here 0.6, and it's the highest among, and therefore it was selected. All right. So now we move on to the next conceptual question. That previous one we looked at what are the steps involved using HMM for language modeling. Now the steps involved using GPT. So these are the steps, right? And let's go into the detail of those steps. So first of all, well, what we basically do is this involves extensive tokenization. Okay, but that's all. This tokenization is based on the context, is much more powerful. Okay, and we'll talk more about it. So what is the first step is pre-process the input. So you need to clean it, we need to make it consistent, for example, and we that may involve lower casing, say for example, which has its own issues if you remember. So if I have capital US and lowercase it to US in lowercase, a different meaning altogether. And if it's apple with a capital A and a lowercase it to apple with a lowercase, different meaning altogether. Removing extra spaces, have their own issues which we have already discussed in pre-processing. Handling special characters which may be indicating emotions and so on. So we do all of this, and then we do the tokenization. We split into tokens the sentence, and the tokenization has its own issues which we already discussed. Okay, so the statement the child is going to might be tokenized if looking at unigram like this. Okay, like this as unigram. Okay, so once we have these tokens, and hopefully we did a good job, these tokens are then passed to the GPT model, which processes them, okay, using the multi-layer transformer architecture, and captures the contextual relationships, which is much stronger, way ahead of n-grams and way ahead as compared to HMM, and then generate the predictions for the next token. Okay, that the next token would be what it's going to be. Okay, and then based upon it, what would be the most likely word which goes after 2. All right, let's move ahead. So and then select the most likely token to fill the blank, and then decode the token, convert into a human, because in GPT numeric values are assigned to the tokens. We'll see in the explanation. So we move on to the actual working, and as you can see that these are the steps, and this is the working of those steps. Okay, and of course if you would like to close all of this, you click on top and you close all. Okay, and we were working with example, I'm sorry, with question number 9. So click on question 9 and click on the description, detailed explanation. All right, so prepare the input text for the model. So this is the input, and we remove the placeholder, this dash. Okay, and then we tokenize, right? So tokens into subwords or words, unigram or bigram or whatever which we want to proceed. So these are the tokens the child is going to. All right. Okay, so let me clean this first. So then we feed the tokens into the GPT model, and the tokens are assigned certain numeric IDs, and of course these are hypothetical IDs. Okay, and these IDs pass through the layers of the GPT model and generate the contextual embeddings. Contextual embeddings. The bank was crowded, so it was the riverbank or it was a financial institution. So it's the contextual embeddings. And then predictions are made for which are, and the predictions are made about the most likely token. So this is the vocabulary. Where do we get the vocabulary? We get the vocabulary from the statements. Statements, which was the corpus also. Okay, that was used for training, and the vocabulary from the statement itself. Okay, so we have play, school, sleep, eat, and the list goes on. So probabilities for the play is you can read the probabilities, okay, and then as before we select the token with the highest probability. It's a greedy approach, and decode the token, okay, into a human readable word because it was numeric ID, and it is mapped back to the word and its play and it is assigned. So token ID 50, which has a this is a hypothetical ID, and it gets replaced for play, and we have the complete sentence. And as you can see that the result was the next word was play by HMM and also with GPT. This is a fairly simple statement, but for complex statements the result can be very different also. Okay, so now contrast and compare n-grams with GPT for language modeling. So we compare n-gram with GPT just to give you an idea that what are the strengths and what is the power of GPT. Because n-gram is good for an academic environment to teach the students basics, but in real life scenarios n-gram may not be a good choice. Okay, and in the next lecture we'll compare GPT with HMM also. Okay, so these are different bases for the comparisons. Let's go through them one by one. So both n-gram and GPT, okay, are language models, all right, but they have distinct and different characteristics. Okay, n-gram is based upon simpler probabilities, okay, and it has a fixed window. It's not dynamic. And GPT is deep learning model. It is not only deep learning, it learns contextual relationships and not distances, not unigram or bigram or trigram. And of course, it is also dynamic. Okay, but it requires, so since it requires more computational resources, it requires CPU power, it requires memory, it requires electrical power also. All right, so let's move ahead. So n-gram is probabilistic, all right, and the word is estimated based on the occurrence of the word following a set of previous words, at most n minus 1 words. GPT is deep learning based transformer and uses attention mechanism that we'll discuss in the next lecture. Not only attention mechanism, but over long term dependencies in the data. Okay, what's the benefit of it? It can model complex language patterns. It means that the result produced by GPT is going to be more human like, okay, as compared to n-gram. Then is the training data dependency. N-gram models rely heavily on the size of the training corpus, okay, and of course they are influenced by the fixed n-gram window, unique by trigram. I'm not going beyond. Of course it can be 4-gram also. And as n increases, the model becomes better at capturing context. Okay, but the thing is that as it goes back, prone to more data sparsity because those words which are used may not be occurring that frequently. GPT is different thing. It is a transformer model and it is capable on training large data sets. And it is not fixed window. So it generalizes better. Okay. And it doesn't have those kind of issues with data sparsity. Okay. Context understanding. It has limited context. N-gram has limited context. Okay. And the context is dependent upon the value of n. This can obviously going to be restrictive for long term or long range dependencies. Looking at 4 tokens in the past or 5 or 6 and so on. So it uses attention mechanism, GPT, right? And it can process the entire sequence. The beauty of GPT is capturing the context over a much longer period or a shorter period, so it's dynamic. So as a result, it's better at understanding the language, and it's better at understanding, and it's better at prediction. For what? Complex sentences, which is not there in n-grams. Sequence generation So this n-gram has a fixed length history, okay, or the window. So if we look at bigram, it would be is going, right, or going to, and so on, which we have already discussed in previous lectures of this course. But GPT generates sequences based on the entire preceding context. So what text is generated, it is more fluent and it is contextually accurate, okay, and it is more human like, right, and it is more useful. Like, all the adjectives are here. So memory and computation, n-gram is not resource intensive. It is simple. It is computationally efficient, means the time complexity is low, and it only stores the frequency counts. Uh, of course, there's a as n grows, the memory requirement will grow, but it is scalable. But GPT is neural network based, and it requires a lot of computational power. It requires memory. It requires electric power also. It stores the weights, right, in the neural network for each layer, and so on. So this is resource intensive, and it has its own dividends also. And finally, the flexibility. N-grams are limited because of their fixed context window, and if there are varying sequences of words with contextual underpinnings, that is not covered by n-grams. As opposed to n-grams, GPT is very flexible. Actually, it's highly flexible, and all I have spoken about it, and it can be fine-tuned also, and it can be task-specific data trained also. So it has variety of applications like machine translation, summarization, question answering, and so on. So this is all for this lecture.